Let's take a look at section 3.4, arguments with quantified statements. This is the last section in chapter 3, and uh, we're just about to begin chapter 4, which deals with mathematical proofs, which is a really important topic in this course. And what we've been doing up to this point is helping to prepare us for that topic, which is a challenging but interesting topic within this course. Okay, so this section actually is relatively short. It talks about the rule of universal instantiation, which takes what we've been doing in terms of arguments and quantified statements and puts those two things together. And what this particular rule says is if some property is true for everything in a set, it is true for any particular element in the set. Okay, we're going to see how that comes up within these arguments that we'll look at. So if you remember back to chapter 2, one of the things we talked about with arguments was we talked about modus ponens and modus tollens as two very important examples of valid arguments. So let's look at a variation on modus ponens. This says all math courses are challenging. Discrete mathematics is a math course, therefore discrete mathematics is challenging. Okay, so this is a type of modus ponens argument. And let me explain why, because there's a couple of things going on here that make it look a little bit different. One is the first premise in a modus ponens is usually written in an if-then form. And this one is not. But you're going to see that come up quite a bit in this section. Because when you're talking about sets, for example, you may, instead of writing it in if-then form, you might talk about how those two sets are related. But let me explain how that first premise could be expressed in terms of if-then. We could say, for all courses X, if X is a math course, then X is challenging. Okay, so there's a relatively straightforward way to rewrite that in an if-then form. So whenever you see that all something are something else, there is a way of putting that in an if-then form. Notice the other thing going on here, which gets into this universal instantiation, is that we go from talking about all math courses to then focus on a specific one. We focus on discrete mathematics. And so if that first premise applies to all courses, then, and we move to the second premise, and now we're talking about a specific course, which happens to be a math course, then universal instantiation says, well, if that first premise is true for all courses, then it's true for this particular course. Okay, that's where universal instantiation comes in, because we kind of shift from the general to the specific. And then the conclusion is discrete mathematics is challenging. So in general, universal modus ponens looks like this. For all x and d, if p of x, then q of x, p of a for some particular a in d, therefore q of a. Okay, that's the general format that we have. But again, that first premise is not always going to be written as if-then. In fact, if you look at the exercise in this section, you'll see several cases where we don't have it written as an if-then, but it could be restated that way. Okay, so universal modus tollens Okay, you can guess what that's going to look like for all x and d. If p of x and q of x, not q of a for some particular a and d, therefore not p of a. Let's look at a specific example of that. All prime numbers are greater than 1. 1 is not greater than 1. Therefore, 1 is not a prime number. And this actually, we will be talking about prime numbers coming up in chapter 4 a little bit. And this gets at one of the built into the definition of prime numbers is that they're greater than 1. So here's an example where we use that part of the definition to conclude that, well, 1 must not be prime if it's not greater than 1. Okay, so let's move on to a couple of invalid arguments. And so you've seen converse error and inverse error back in chapter 2. And this just takes them and works in that universal instantiation aspect where we go from talking about all elements of a set to focusing on a specific element. So the converse error would look like for all x and d, if p of x and q of x, q of a for some particular a and d, therefore p of a. Okay. You're going to see in the exercise in this section, there'll be arguments where they ask you to identify, is it valid, is it invalid, and if it's invalid, is it the converse error, is it the inverse error? Okay, the inverse error, okay, if you remember from chapter 2 and kind of work in that universal instantiation aspect here for all x and d, if p of x and q of x, not p of a for some particular a and d, therefore not q of a. In a separate video, we're going to look at some examples, including an example where we look at how Venn diagrams can be used to evaluate validity for certain kinds of arguments. The next section of the course that we get into begins our look at proofs, direct proofs, and counterexample 1 is the title of section 4.1. That'll be coming up, and I look forward to starting that topic with you. We'll see you in the next video.